We're live, we're live. We're live with live hacks. Um, Part of our goal today is to just give tips to developers interested in learning how to build on Polkadot. And so you're in the right place right now if you want to learn about building decentralized applications with the latest features of Polkadot. My name is Sacha, and I'm here today to host an amazing person that's been doing amazing things building with the latest features of Polkadot. Now, before we get into that, I want to just give you guys a little bit of an insight on who am I and what I've been also working on, which is, well, I've been really busy working on the Sub-Zero hackathon over the last couple months, which is happening in Buenos Aires in a week and a half. It's happening on the 14th of November, and it lasts for 3 days. It's probably going to be the biggest in-person hackathon for the Polkadot ecosystem. And so I wanted to just give you guys a little bit of a teaser on what to expect. So I'm going to share my screen and just give a little bit of an insight on. Ooh, I need to share my screen. 1 second. We're going to go like this. Yes. So right now we are actually looking at a hackathon that is involving different types of innovators in the ecosystem. So if you are going to be in Buenos Aires next week, sign up here. It's luma.com/subzerohack. And our whole model, guys, is that we're trying to bring engineers, developers, and non-technical people, marketers, product leads, and BD people all in one place to drive innovation in the Polkadot ecosystem. But that's not it. We actually have a lot more going on than just Polkadot technologies. We have a partner track from Archive. We also have a bunch of different bounties from Hyperbridge. There's a Kusama bounty, and also from our partners at XX Network, fully private, preserving post-quantum encryption technology. How cool is that? Finally, there's a marketing track. So that means that if you're participating in this hackathon, you're a marketer, you feel like you're maybe not a very technical person, you are as important as a developer in this hackathon. So now I think that this section here on Kusama and XS is a really good segue into what we're going to talk about right now. On this stream, as many of you might have noticed, we're going to be building a ZK application with Ethereum tooling, with tooling that is very common in the Ethereum world, called Noir, by a company called Aztec. And we're going to actually bring that in to an Inc smart contract. So I just wanted to debunk what all of these terms are for people that are maybe new to building ZK applications before we bring on our very special guest. So real quick, well, there's this programming language called Noir that is built by an ecosystem called Aztec, right? So Aztec is a privacy-preserving infrastructure in Web3 that primarily focuses on making it really easy to build ZK applications, to build let's just say the inner workings of a ZK application. So if you're new to the ZK tech landscape, what that really boils down to is, well, you need to build a piece of software called a circuit that is a lot of mathematics, really, really hard to do if you don't have a good framework to do it. But these people make it super, super simple to actually build. So the language itself is a Rust-based language. And we're going to dive into what that looks like and how you can bring that into your Polkadot application. Now, how would you bring this into Polkadot? Well, it turns out that right now, there really is only one way to build that into a fully programmable Polkadot application, and that is using Inc. Inc is the native smart contract language to the Polkadot ecosystem that currently has all the features, like battery packed with being able to do all of the cross-chain interactions you possibly can imagine out of the box for people building dApps on Polkadot. So a real quick shill to the Inc team that just released all of these features actually 4 days ago. And our host here, Lynette, that's going to come on just in a second, has gone through the pains of or I don't think it was really painful. We're going to learn about that, but she's basically taken the latest of ink and went through the process of building a dApp that integrates a Noir circuit with an ink contract. So ink is a Rust DSL, and if you are a Rust developer looking to build in the Polkadot ecosystem, it is probably your go-to choice. Now, why not use Solidity all the way? The thing is, you can, but right now, the compatibility with a lot of the Solidity stuff on Polkadot is not as up to speed as it is with the ink language. As you can see, 4 days ago, there was a release that actually allows you to call a Solidity contract from an ink smart contract. I'm going to repeat that. You are able to, from a Solidity contract, call into any Solidity smart contract. That is really cool. That actually gives a lot of superpowers to what we're able to do. So a quick recap. Noir is a domain-specific language for writing zero-knowledge circuits developed by Aztec Labs. And it's designed to write, to make these ZK-proof applications much more accessible. It's a lot easier to do, as well as it gives you a lot more flexibility as a developer to integrate different proving systems. We're not going to go really much into that. We're trying to keep things high level. And then I want to just highlight what the ink capabilities are. So ink is a smart contract language for the Polkadot ecosystem. And right now, you are able to do cross-contract calling between an ink contract and a Solidity contract, thanks to this new the features that the ink team has released that allows you to, with a simple macro, be able to call into a Solidity ABI. That is really powerful. And now I think this is a really good time to bring Lynette on, our very special host, who's been working on creating a small educational piece to show you guys how to do that. How's it going, Lynette?
Hi, Sasha. I'm good. I'm doing good. How are you?
I'm stoked. Like I really am stoked. I had I had some time to prepare before our chat here, and I was like, I realized that this is very, very new stuff, and it's not really possible to be doing the work that you're going to present until just 4 days ago, really. And so like I wanna hear, first of all, I wanna take the time to hear a little bit about your journey. Like, how did you get to being curious about tinkering with this kind of tech, and what led you to caring about building privacy preserving applications?
Okay, so hi, I'm Lynette for the viewers. And I started my blockchain journey about like 3 years ago. And of course, I started with learning Solidity, smart contracts, programming on Ethereum and deploying them on Ethereum. And then eventually, I, of course, got a job and was implementing a DAO on Hedera. And through doing all this work, I was more interested in other ecosystems. So I started exploring Stacknet. And on Stacknet, they use Cairo, which is a Rust-based programming language. And that was the first ecosystem where I heard about zero knowledge proofs, and I was very interested. So in April 2024, I started learning the math behind cryptography in general, so stuff like elliptic curves, and then implementing them in Rust. And then all by learning about cryptography, I was also interested in blockchain architecture, understanding how it works, understanding how to build it. And I found myself stumbling onto Polkadot. So on Polkadot, of course, you come across Ink, which is the smart contract language for Polkadot SDK chains. And earlier this year, actually, I think it was like 4 months ago, I was trying to implement a project to practice my skills on Noir and Ink. And I was thinking, why not deploy this application on Polkadot? So I, of course, started my little project, wrote the circuits, compiled. And then when it came to now writing my application logic, I realized that this would be a very impossible, almost impossible task to do, because with Noir you can only have either a Cairo verifier or a Solidity verifier, not in ink. And then if my app logic is in ink, that means I can't call the verify function directly from my ink smart contract. So a few months ago, I had to put a halt to this project, but with the updates that Ink has introduced, it means that I can now deploy my Solidity verifier on Poker VM and call the verify function directly from my Ink smart contract. So that's how I got here.
That's really cool. Um, I think like what you're describing is just like a common thing in the Polkadot ecosystem where there's always some new stuff that's coming out really fast, and it's hard to like keep up with things. So and I guess like I'm curious, like, can you share a tip about like what you like what you could give other developers that are curious and keeping up with the latest stuff on Polkadot? Where should they go? What should they be reading?
On Polkadot, right?
Yeah, like how do you keep up with like the latest stuff? How did you know that this was actually like released and ready for you to test out?
So actually, I think I was thinking about this before this stream actually, and I think that one of the best resources that you can use as a developer to stay up to date when it comes to Polkadot is the Polkadot forum. So a lot of times you find that updates are usually posted there when it comes to different tooling that is used on Polkadot, the infrastructure itself, the community, everything to do with Polkadot. There are always forum posts on it, or more often than not, there are forum posts on it. And also keeping up with the X channels, X, what are they called? Yeah, channels,
Yeah.
which is Twitter, that is. So I remember I actually heard about this, the Ink Solidity ABI. I heard about it first on their X page. They posted an update, and I was like, this seems interesting. Where can I read more about this? Provided me with a link to the GitHub issue that had all the details to do with this. And that's how I know about it.
Yeah, cool. No, thanks for sharing. I mean, part of my objective on this kind of stream is to give tips for other developers that are like yourself, like, you know, finding their way and at building things. And so I think that's really great advice. You know, there's support channels. The forum is a good place to know where stuff is being updated, and people are going to help you in the chats if you're going to ask your questions. So I'm going to share my screen now. I think we can get right into it. The first thing that I want to share is this meme. Like, I think not only I'm really keen on having you just like share the journey of building this kind of paradigm of an ink smart contract with a Solidity verifier, but I want to kick it off with this and ask you, like, what is important right now about building privacy preserving applications, and why should developers really care about it?
Of course, privacy is a very important aspect when it comes to the applications that we use online. And it's not just about security, it's more about you can think about something like how we use the internet these days with the HTTPS. Before we had HTTPS, there was just HTTP, meaning that it was not that secure. But most people, more of like the layman, didn't care a lot about that. They didn't see the issue with that. But right now with HTTPS, you're able to use the internet more securely, and imagine you're not easily getting hacked into your computer because of such protocols, and you hardly ever notice that it's running in the background. So that's the case also with privacy. We want to make sure that your sensitive information is not being accessed and used maliciously. So as much as we want to be able to provide verifiable information on the internet, we also don't want to have our personable information available for malicious use. So that's why most developers should actually care a lot about zero knowledge, and not just zero knowledge, more like cryptography and developing privacy preserving apps, uh, because it's better for everyone, and it actually aligns heavily with the ethos of blockchain.
Yeah.
So with blockchain, we just have what is known as anonymity. So if you have your address, typically people won't really know it's you unless you make it public. But there's still a lot of information that's attached to your account. But with privacy, we're just making sure that we have selective disclosure. Only the information that we're sure will be necessary for verification is available.
Yeah, absolutely nailed it. I think like we have actually been for many years developing Web3 in a way where we're forgetting, I feel, the ethos of the need and like the necessity to have privacy preserving technologies baked into what we're doing. And I think there's a good reason for that.
Yeah.
And the reason is that all of these ZK libraries as developers, they didn't really exist 2 years ago. I think that the first real versions of libraries that developers could start tinkering with, I'm talking about not the infrastructure layer of ZK tech, the actual like consumer facing, potentially like this is an application using ZKPs out of the box kind of tech. That's been really hard to do, right? Our paradigms are you generate your verifier contract, you put a verifier on chain, and now you can use it. That is easy to do now. Today it is, thanks to technologies like Aztec developing this, right? But in the past it wasn't. And so I just want to stress that it's so important. People that are at hackathons right now building their tools, think about building privacy preserving solutions, at least solutions where confidentiality is at the backbone of what you're building by choice, by default. It has to be a default choice. And so I think, yeah, I just want to lead into our next section here by emphasizing that. If you're at a hackathon, make use of the bounties that are going to encourage you to use these technologies, because that's where the future's at. It's not just permissionless DeFi. So with that said, Lynette, what do you think? I'm going to quickly go over the repository that you prepared for us. And then it's the stage is yours. So this little repo that you prepared has the contracts for the business logic of the chain and the verifier contract and the circuit here. So you're going to explain all of this, but the purpose of me just showing it like this is for the audience to see. You can clone this repository yourselves. Check it out while we're going through things. I'll share a link in the chat so that everyone can see it. Is there anything you want to add before we move on to you sharing the screen, Lynette?
No, we can go right ahead into that.
Okay, well, I'm gonna then stop sharing my screen and you can have yours prepped up so we can get into it. So yeah, I mean, one thing that we didn't really explicitly talk about is what are we really building today? And well, in the world of privacy preserving decentralized apps you can build, a really popular thing is anonymous voting or anonymous sending of payments, or yeah, privacy preserving on either the financial transaction or any other transaction on the chain. And in our little demo, we're actually going to go over a anonymous voting type protocol that Lynette has prototyped for this stream. So Lynette, you need to just
Okay, so I'll just
there's a screen sharing thing on the bottom, and then that's how you get it up. It's got an arrow.
Can you see my screen?
Yes.
Perfect. Okay, so actually, I think you did a very good job of giving the background on zero knowledge and privacy preserving applications. I had prepared something small, but we can, since we've already covered all of this, we can just talk about the project that I will be demoing today, and that is an anonymous poll app. So I think when most people start building on blockchain, actually, they start with voting, a voting application, because it's one of the use cases that is very easy to implement and also needs that a decentralization. So what I was doing when when I was trying to learn or trying to practice my skills in Noir and Ink was to build a voting application that is privacy preserving. So in this case, we just want something that proves that somebody has voted without revealing their vote. We don't need to know who or which option you chose, but we just need to be able to verify that you have already cast a vote. And then another thing, I think I'll just move to the GitHub repo right here. Another thing about this project is I'm also implementing the concept of nullifiers to prevent double voting, and that will also be implemented in the circuits that we have. So currently, I'm just going to
We're-
start off
We'll go
from the
over
circuits.
nullifiers, right? We'll go over nullifiers.
Yes, yes, yes. So, okay. I have my circuits. My circuits are written in Noir, as we already mentioned. It's a Rust-based programming language for zero-knowledge circuits, and it's very much like Rust. So if you're a Rust developer, you probably won't have a hard time understanding how to use or how to write Noir circuits. But remember that circuits are made up of what are known as constraints, and constraints are just mathematical conditions that need to be satisfied in order for proof to be valid. So in our case here, we have some uh, constraints, and in this case, they're in the form of assertions, so assert statements. We want to make sure that, for example, in this case, this is one of the constraints, sorry, this is one of the constraints, and it's calling this is valid member, which is checking and confirming that the person that's trying to vote is a member of or is an eligible voter. So when you're creating a poll on this anonymous poll application, you have to specify the eligible voters. So you will pass the values in the form on the front end, and then a Merkle root will be generated from these values. So when we're trying to verify whether this voter is an eligible voter, we have to use the Merkle root, and the leaf in this case is the identifier, and then the path, and we have to make sure that the path leads to the Merkle root. If it doesn't, then that means that this voter is not a member of this list and they cannot possibly vote. So I also have some helper functions that perform this checking, like to verify the Merkle membership. That's pretty much what's in the constraints that are in my NOR circuits. Also for checking about the nullifiers, so we want to make sure that the nullifier that our voter is using was computed correctly, and our nullifier is being calculated from the Pedersen hash, which is a function that's provided. It's a hashing method, a hashing function, sorry, that's provided by Noir. And the way we're doing it is we're passing the user secret or the identifier and the poll ID. And how this nullifier works is when you're voting, your nullifier will be put into a mapping that to assert that you have actually cast a vote. And when you come to vote again, the our program will check whether your nullifier already exists in this mapping. If it does, then you cannot vote again. And if it doesn't, then you will cast your vote. Um, and then the reason
So
why we're using the
I'm
poll
not
ID
sure.
to
I think we can just explain a little bit better the concept of a nullifier. Like how is this? You know what? Actually, I'm going to even take a step back. I want to just really clearly explain for our listeners here that what we're looking at is the constrained environment that is going to be checked against when we're going to write out the business logic is going to say, like, for example, this account is going to make a vote. That account needs to be part of this set. Now, so this circuit is a constraint, is containing the accounts that must be in this set, right? So my first question is, do we have to already pre-specify the accounts that are going to be in this verifier contract? We do.
Yes,
And
we do actually. So as I was,
yeah,
okay,
please.
I could actually explain a bit on that. So when the application is complete, this ZK anonymous poll is complete. Of course, in the front end, we need somebody to create the poll. And when we're creating the poll, we're not going to directly ask them for a Merkle root or a leaf. They're probably not technical enough to do that, but they are going to provide us with a list of eligible voters. And from this list, we will be able to create the Merkle tree and get the Merkle root that will be used in our proof.
Yeah. But all of this is done before you generate the verifier contract.
No, the verifier contract is already deployed. So we're looking at it as an application that you're using. It's already ready. You have it probably on your phone. So that means that our verifier contract is already deployed. Now, what happens is we have the witness, which has a set of all possible inputs that will satisfy our constraints. And with the witness, you can be able to prove that these values that are being passed are valid. And
Mhm.
there's a verification key that helps with the uh, verification of the proof, a
Okay,
VK.
yeah.
So while we already have some witnesses, while we're using the app and we're passing the list of eligible voters, our contracts are already deployed, they're already on chain, they're already ready to verify the proof and verify that the voter is eligible, one, and that they have not already voted.
Very cool. Yeah. So just to recap, what we looked over is the Merkle tree implementation, which is basically a lookup on the accounts that are eligible for voting, and we have a nullifier, which
Yeah.
is sort of like a flag that enables knowing whether that account can vote again or not.
Yes, yes. And then the nullifier is actually specific to a poll. So while you cannot vote twice on a poll, that doesn't mean that you can't vote in multiple polls. That's why we're using the poll ID to generate the hash of the nullifier, or passing it to the Pedersen hash function, because we want to be able to vote in multiple polls. If we were to use just your secret to generate your nullifier, then that means you would only be able to vote in a single poll, which is not what we are going for.
Cool. Cool. Thanks for clarifying. This is great.
Okay, so with our circuits, once you have your .noir file, which is our circuit, the functions in the Merkle.noir are already in this main, so that's why I'm not looking into it. Like the verify Merkle membership is the same on here, so I'll not look into that if you're wondering. And then once we have this, we can now compile our circuits. And once you compile, you'll get the witness file, which is what I mentioned before. It's just a set of all possible inputs that would satisfy our constraints that we have already specified here. And then the if you look into my IDE here, the .gz file, that's the witness. And you can't really see into it because I believe it's in bytes form.
Yeah.
But once you have that, you can generate our proof and a verification key. So the reason we have a verification key is so that we don't need to use our witness to verify a proof. Remember that the witness has all these public inputs that are valid. So if we expose this witness, then it beats the point. That means that anybody can just go pick valid inputs from there and probably generate a valid proof when in a situation when it's not ideal or when it's not organic. That's what I'm going for. So what our verification key is a smaller bytecode file that helps us verify our proofs, and then that's what will be used to generate our verifier contract.
Yeah.
So this our compiled circuits are also what will define how our verifier.sol file will look. So once you've already generated all these files, like our verification key, which is the most important, you can generate your Solidity verifier, and it's placed into the target folder, this target folder. And here is the file, verify.sol. So if you
So real
actually look
quick,
at it, it's very huge. Yeah.
yeah, real quick. All of these files are generated, I assume, with a Noir command or something that comes with the Noir language,
Yes.
correct?
Yes.
Including
Yes. So
contract.
actually, the yes. So the verifier contract is actually generated by the proving backend, which is known as Barrett and Bug. That's the proving backend that is the default one on for Noir. And if you just check the docs, you can find the command. It's just a single line command. Let me see if I can find the docs. Are they? Okay, so these are actually the docs for Noah, and if you follow them, you can create your fast privacy preserving circuits or ZK circuits, and then ooh, okay, if you want to generate your Solidity verifier, you open the Bartenberg docs
Nice.
here. So this is a command. As you can see, we're first of all we're generating our verification key, and because we already have that, we don't need to run this command. Once you have your verification key, you're going to pass that verification key as an argument to this command where we're generating our verifier.sol uh, file contract. That's it, basically. This file, it's really long. It has almost 2,000 lines of code. And basically, what's in the verifier.sol, um, think of it as like elliptic curve cryptography or calculations, the operations that handle the math of verifying proofs. And because they're so complex, you probably cannot write this for every contract, every circuit that you have. So it's easier to just generate it directly from your verification key. And the thing about the verifier, it exposes one function, which is what you're going to be calling from your app logic or the business logic of your app. And that function is called verify.
The very beautifully elegant
So this
verify
function here,
function. Actually, do you
yes,
mind
this is the only
zooming a little
function
bit
that,
so we can see the contents of the contract that you're showing? Control plus or
okay,
whatever.
sorry. Let me just actually, let me, wow.
A lot of tabs.
I want to just,
I love how
yeah,
you keep your
that's
search
actually how,
panel on the right side of your screen. It's really off. It is almost like confusing for me because I always have mine on the left side of the screen, and I always have. But I love it. Different developer environment settings. Yeah. So okay, like quick
I
recap. We're
actually
looking
have,
at the verifier dot. It's the Solidity contract that is generated
yeah,
once you generate the verifier contract from the Noir tool set. And what we're looking at is it's a whole bunch of things to do with complicated maths, but what we really care about in this function is the verify function, and that's what you're. Yeah, perfect. So I'm
okay,
assuming, Lynette,
so yeah,
you're not going to really go and modify things in this contract. Once it's generated, that's it. Like, don't touch it.
yes, exactly. So once you have this verify.sol file, you don't need to update anything inside it. It's already customized to your circuits because you generated it using the verification key. The only thing that you need to worry about in this smart contract is a verify function, which is what we're going to be calling from our Inc smart contract. So if you're writing your business logic, you of course need to pass the values that will be verified, that will create a proof that will be verified, and you do that through this function called verify. right here. And the arguments that it takes are just an array of bytes for public inputs and bytes for the proof, and it will return a boolean. So either the proof is valid or the proof is not. So true, false. That's it.
Cool. Well, I'm really excited to jump into the ink stuff. I think, yeah, we're pretty close. Is there anything else we wanted to go
Yeah,
over
actually,
contract?
yeah. So before that, actually, you need to deploy this. We need to deploy this on Polka VM. And to do that, it's very simple to use Remix. So I pasted the same smart contract on Remix IDE and then compile it. So in order for such a long smart contract, if you want to compile it without any errors or warnings, you have to turn on optimization and then just compile your smart contract, and then you can deploy it. So I had actually, we could deploy again, just deploy again. So there are no uh, initial values that we need to pass. Okay, sorry. We need to choose the honk verifier. That's if you look into the smart contract, let me show it on this side. We have a lot of abstract contracts inside, but the actual contract that we're going to be deploying is the honk verifier, because there are abstract contracts like the base honk verifier, and that one is not what we are going to be focusing on. So you just select honk verifier and then connect this to your MetaMask, and of course we want to make sure that MetaMask is set to Passet Hub, Passet Hub, and you can add it. So remember how I said that you can find all this information on the forum? There's this forum post that talks about the Polkadot Passet Hub testnet, and it has all the information about adding it to your MetaMask. So you just need to pass the URL, which is this one. Which one is it? This one, the ETH RPC endpoint, native token, and the chain ID. And once you add it, then you have Passet Hub on your MetaMask, and you can claim some pass tokens from the Polkadot faucet. You'll get about 4,999. So just choose Polkadot testnet Paseo, then Passet Hub smart contracts, and pass in your contract address, which you can find here.
I think it's so cool how now we're seamlessly using MetaMask with Polkadot. Also,
sorry, these addresses. Sorry, yeah. Once you have your address, just choose this one for Paseo Passet Hub and paste it here. Confirm that you're not a robot and claim your testnet tokens, and then you can be able to deploy your smart contract.
nice.
That's and yeah, it's actually very cool that we can use MetaMask on Polkadot now. So now I have my pass. Let me just check. I had like 1499. Should update. I think it will with time. But now, if when you have your pass tokens, and you've already connected it to Remix, then you can deploy your smart contract.
Yeah, super cool. I mean, the Remix tool, very useful for people that want to quickly deploy a contract that's maybe like copied over from somewhere else. You don't need to do it from your from your IDE directly. Sometimes you need additional setup to do that. I really like how this was your go-to choice. It works really well for you, and that's what's important, right? Use the tools that work well for you, and don't over-engineer things if you don't need to.
Yeah. So this green check mark means that we've been able to deploy our smart contract. I think we can find that on here.
Right. So what we're looking at here is Block Scout, which is the block explorer for Passet Hub currently. And so a tip to everyone who is watching, who might be wanting to do this themselves, this is the Block Explorer where you can see your contracts live and all the other accounts that interact with it.
Yes, exactly. So now here we can see the transaction for our contract deployment. As you can see, this address is the same address that we have here. So the address that I've used to deploy. And then here is our contract address. And this is going to be what we'll pass to our constructor on the Ink smart contract to tell it that this is the contract that you're going to be interacting with. So as a constructor, we're going to be passing this H160 address. Yeah. So don't throw this away. Just keep it around, safe. And then with that, now we can actually move to Ink.
Let's do it. That's what I'm most excited for. And yeah, for the sake of time, let's get right into the Ink stuff.
Okay.
So like while you're setting it up, quick recap: we have our verifier contract on chain. We know that the function that we really care about is the verify function, which takes in some bytes, takes in some other information. Lynette will go into it. And right now, it's about using Ink to call that function. But more than that, Ink is going to be doing like the business logic stuff, right?
Yes. So if I open my smart contract, just right here, my Ink smart contract, you can see we have the struct for the polls, how they're structured. Then we have errors and events for poll creation. You've cast a vote, poll has been closed or it has come to an end. Then we implement this function. So the first one is the constructor. And as I mentioned, for our constructor, we're going to pass in the address of our verifier smart contract. And that's what we're going to be using to instantiate our our Ink smart contract. And then we have functions or messages, we call them messages, for creating a poll. We have some for casting votes, casting a vote right here. And in the cast vote function is where we're going to be calling, where is it?
Yeah.
The call verifier function. It's another function that now calls our Solidity smart contract. So call verifier, pass our proof that our public inputs are here. We've already encoded them and we have already gotten our proof. It has been passed as an argument for this function. And then we're going to pass that to our call verifier function, which is this one right here. And it's for calling our Solidity verifier contract. So with the call verifier or calling our verifier, initially what we had, of course, with Ink, the previous versions of Ink, you could do cross-contract calling. That is from an Ink contract to another Ink contract. But now you can be able to call Solidity. So before we had this, or we still do have it, the build call method, which is specific to calling another Ink smart contract. But if you want to call a Solidity contract, then you have to use this build called Solidity, and then pass the values for like the address, the values that the arguments that we're passing, what we're expecting to be returned. In this case, it's a Boolean, of course, from the verify function. And this is just for error handling, the try invoke method. And then for selecting our function name, we're using selector bytes, and then we say verify, which is the name of our contract, and they're both returning bytes, or they're both receiving bytes. So this is actually the most significant part of a smart contract that's calling another Solidity smart contract. Instead of using build call, you'll use build call sol. And then another configuration that you also want to make sure you've done is in the cargo.toml, you want to specify the all ABI, either all or sol. So ABI is a standard for interacting with contracts, and it basically defines how you can interact with that other smart contract when it comes to things like encoding and decoding data. So the default when you start a new Ink project is Ink. And that means that it will use the scale encoding method or scale codec by parity for encoding input and output, and other specific aspects of ink. But if you specify Sol, then that means it will use the ABI encoding method for encoding and decoding our data. And it will also require you to have a single constructor in a smart contract. And the cool thing about ink is that you can have more than one constructor in your contract. But if you're using Solidity ABI, then you have to specify a default one. You can have multiple constructors, but you have to label one with default so that the Solidity ABI can be able to identify which one it will work with. And then in the case of all, which is what I have here, that means that it will generate ABIs both for ink and Solidity, which of course is more expensive for you as a developer. It makes your contract size bigger. But I used all actually so that I could get the .contract file and deploy it on the contracts UI. If I were to just specify Sol, I would get the test.abi, and for that .abi, I wouldn't be able to deploy it on the contracts UI. So
Right.
once you've checked on this, you're pretty much ready to go.
Yeah. Just quick recap.
Yeah.
Contracts in the Solidity world have a different way to interface with them than contracts in the ink world natively. Ink allows now the ability to interface with the Solidity world as well as the ink world.
Yes. Awesome. So okay, I had already compiled my contract and gotten these artifacts, but we can just do it again. Cargo
Well, maybe
contract
we can skip
build.
the deployment stuff. Like, I want to hear about the contract itself. So you mentioned the verifier logic. I had a question. If you don't mind going back, my question, no, in the ink contract, you have a function that is call verifier, exactly. So would you say that people that are going through the same pattern of deploying a verifier contract in Solidity and wanting to call it with the ink contract, are they basically using the same kind of boilerplate code for this call verifier, or is there things that are very unique to your application in call verifier here?
Okay, no, actually for the call verifier, I would say it's very much boilerplate. Other than no, actually it's very boilerplate because the function that we're calling is verified.
Yeah.
Yeah.
Yeah. That's what I thought. I just want
Yeah,
to
it's
make
verified.
that pretty clear because I think it's also an opportunity to create templates with this basic pattern for people to just understand. Maybe something that we can give to the ink team, because it's always the same pattern, right? With ZK apps, you
Yes.
create a verifier contract, deployed on testnet, and then you have a contract that interacts with it that is going to have the same function to call that verifier contract, no matter what the contract is. So, yeah.
Yes.
Now, talk to us a little bit about. Sorry, go ahead. What were you going to say?
Oh, I just wanted to mention that since every verifier contract has the verify function, and the verify function looks the same for all of them, they are all receiving proof that is bytes, and public input is an array of bytes. So it's pretty much going to be the same for all call verify functions.
Mm-hmm. So now, on the more like application specific logic, can you run us through what's going on in this contract? And what are your tips for creating similar things creating a similar application that is to interact with a verifier contract? So I know, so we're talking about anonymous polling system. So obviously there's creating a poll, putting the addresses that are valid addresses. I'm just kind of going off the top of my head, but maybe you can lead this here, and we can just shed some light for our listeners here.
Okay, so for the create poll, actually we're not directly passing the members onto this function, because that would mean a lot of storage being used. So what we'll have in the front end is just a script that does the calculation of the Merkle root from the list of members. And then that Merkle root is what will be passed to creating poll, to the create poll function. So in the front end, a person is giving us the title, description, list of members, the maximum number of options that can be chosen, and a duration for their poll. But to the smart contract, we're going to pass a Merkle root. That means that our user input is going to go to a script before the values are passed to the smart contract. Then once we have our values, we of course emit an event. We'll have to emit an event that a poll was created. Then we have the cast vote. Of course, first of all, with casting vote, we have to make sure that the poll is still active. Here, that the poll is active, that the time frame has not ended for that poll, because if the time frame has ended, then the poll is over and you can't really cast a vote. Then check if the vote option is valid. If the maximum options were, let's say, 5, then you can only choose maybe like 0, 1, 2, 3, 4 options. That is what would be passed here. And then here is where we're checking if our nullifier has been used, the nullifier of the voter. And that's gotten from the identifier and the poll ID. And then we want to make sure that it's not already present in the use nullifiers mapping. So we have a mapping for that. And if it's present, then of course you can't vote. Then we're preparing our public inputs to that will be passed to our verify function. And for that, we have the Merkle root, which is what was what was passed. Not here. It's actually in the specific details of the poll that they are voting in. So remember that all this data was stored in a mapping or in a struct. And then we fetch the Merkle root. We have the nullifier for this specific voter. We have the poll ID that they're trying to vote in and the max options. These are the public inputs that we're going to pass. We're going to encode into bytes first, and then we're going to pass it to our verify function. And then we call our verifier contract to validate the proof and make sure that it's valid. And if it's valid, then our vote will be cast. And then this is just like cleaning up, making sure that the tally is up to date and the total votes are also up to date. And then emit an event. That's really the logic when it comes to casting a vote. Then we've already looked at this function.
Cool.
These
So I know you wanted to actually build the contract live, but I think for the sake of time, maybe we can skip through the steps that might take a little bit of time. And do you want to jump right into, okay, well, you've got both things up on chain. Do you actually have them already deployed, and you can show us how you would interact with them?
Yes, so I already deployed the Ink smart contract, those multiple versions.
Nice.
But this is the latest. Okay, so
we're looking at the contracts UI.
what was I thinking?
That is ui.use.inc. That's like your go-to place for Ink contract development to actually see the contracts there.
Yeah, and when you come on the UI, you want to make sure that you're connected to Passet Hub, Polkadot Passet Hub, and you're using Ink version 6, because remember that we're using the Ink version 6, which is compatible with Polka VM. And then you'll upload a new contract code, which is the .contract file that was generated. And once you've deployed it or instantiated it, we can now call each of these functions that we had. There was create poll, cast vote, get a poll, details. All these functions are now available for us to use. So let's try and create one. Maybe poll. I'm trying to think if I can get oh, okay. I think I had a Merkle root in my prover.toml. I'll just use that. And then pass it here. And then I'll just put max options at 5. And you can already see that the dry run already tells me whether my contract call will be successful or not. Then duration, maybe 120,000, just a value. This is in seconds. Then we can call that function. Yeah, so it's going to, success. So we have created a new pool, and we can fetch the details for that pool using the get pool function. Just write one.
So what? Oh, I think we lost the net there very suddenly. I was gonna ask, what is the way to specify which accounts can actually join? Let's see. Maybe her laptop died. Well, we'll give her a few minutes. And yes, we're back.
Oh my God. I hope I didn't drop off for too long.
It was so anonymous, your application, that you just dropped off to cast your vote. And yeah, I mean, really great implementation. I don't know how you did it. Maybe we can just get back to what you were showing, and then
Okay.
cool.
I guess the implementation was a bit too good. Even the internet respects my privacy.
Exactly.
Yes. So
all right, contract UI. We've created a poll, and now we're ready to actually show it in live. So I actually had a question, which was, where are the accounts specified that can participate in this poll? That was in the Merkle root, right? But you just pasted in a number.
So,
you said, oh, I generated this offline. So as a developer, what do I need to know? Like, where am I generating this, and how does it work?
So there's actually, I believe I have a script for that. I don't know if I've pushed it to GitHub, but there's a script that I have. I wrote it, where you can just pass the values to the function, and then it will generate it will calculate the Merkle root for you, and then you can use it. So in my application, that's basically the script that will be running in the backend to generate a Merkle root. So for now, I was just using a Merkle root that I already had and had used in the prover.toml file, just because of time. And I don't think that script is quite fresh, but I will add it to my GitHub repository, which has all that logic.
Awesome. Yeah, like after this stream, feel free to let me know, and we can share it around. This is great.
Okay. Yeah, so we've created a new poll, and we can be able to fetch the information basically about it. That it exists. This is the poll ID, name of the poll, a description. This is the Merkle root, maximum number of options. This address here is the address of myself, the creator of this poll, which is my account on polka.js. I believe when it's mapped. And then this true just indicates that it's still open, and the number of votes, and then the start of the poll and the end time of the poll. These two are time. So pretty much you can interact with any of the functions that are here. You can also update the verifier contract that you want to be called by our smart contract by passing a new verifier contract address. So let's say you deploy a new Solidity smart contract, a new Solidity verifier, and you want that to be used instead for whatever reason, then you would pass that address here and it will be updated.
Okay, cool.
Yes,
that's really neat. Yeah.
Yeah.
I think we went through everything. I think, yeah, I think we're
Yeah.
good. Like in terms of like presenting everything that you created so far, I want to maybe let's leave the stream with a couple like tips that you might have. Maybe you can stop sharing your screen and yeah, like so first of all, thank you so much, Lynette. That was really cool. I think you've demonstrated a solid understanding and also communicating the patterns of like building a ZK dApp with ink. Like this has not been done before because ink
Yeah.
doesn't have compatibility with all of the Solidity and EVM type ZK tooling. And so now you can do this. And so this is really, really awesome. I want us to like iterate on the repo together. Maybe we can, make some more examples. That'd be really cool. But before we just tune off here, what are your tips for developers that are tinkering with ZK applications on Polkadot? What do you want to leave the audience with in terms of, there's a bunch of people participating in the online hackathon right now, a bunch of people that are going to come to Sub-Zero Hack. What are your tips for builders in general? Like, you seem like you're someone with a lot of experience. You've figured out your own way in the Polkadot ecosystem, and I think that's tremendously valuable for people like you, or people that are looking to take the same path. So yeah, please share any tips you want to leave the audience with.
Okay. So first of all, I hope you can hear me well. Um,
I can.
okay. So I think the number one tip I would give developers or ZK developers on Polkadot is, first of all, you need to understand that this is very new to the Polkadot ecosystem, and not just even Polkadot in general. ZK and cryptography are very new. People are still working on ways that they can optimize them. So as a developer, when you're trying to, let's say, tinker with new stuff and you encounter a problem that doesn't have a solution that exists, then feel free to start implementing it. Start thinking about doing such a project, because it means that you've identified a pain point that probably developers are going to face in the future. So even in something like the Sub-Zero hackathon or Road to Sub-Zero, whatever hackathon you're participating in, you might want to build on those pain points, so that it's possible in the future for people to deploy their privacy preserving applications on Polkadot, because that's what we actually need. So just identify your pain points and leverage on them. There's always going to be support for building this stuff because we all want privacy.
I think that's an awesome way to end the stream. Thank you so much, Lynette. And I really appreciate the time and effort you put in this and sharing your tips to builders in the current hackathons. I look forward to seeing you soon. I think we'll be seeing each other in Buenos Aires. And to everyone else planning to come, don't be a stranger. We're going to be around, and come talk to us. So thanks a lot. Cheers.